And so now we head back to the US, but this time we're heading to the East Coast where it is very early in the morning for our next speaker, which is Professor Michael Golay from MIT. So Michael is a professor of nuclear science and engineering at the Massachusetts Institute of Technology. He is the director of the Reactor Technology course for utility executives and Nuclear Operational Risk Management course, both co-sponsored by MIT and the National Academy for Nuclear Training. Most recently, he's focused his research and teaching upon improving nuclear power performance, both in the United States and internationally, particularly through the use of probabilistic and dynamic methods of analysis. He has also been an active advisor to governmental and industrial organisations, particularly concerning risk-informed regulation and nuclear non-proliferation. So, Michael, thank you for being up in the wee hours of the morning for us. I'll leave the floor to you.
Can you hear me?
Yes, we can hear you. You're a bit quiet though.
Oh, all right. I'll try to I'll tune it up a bit. There we go. Okay. So what we'll do is have someone in your end go through the slides, and I'll narrate the things I want to say about them. Okay?
Perfect. I'll change the slides for you.
All right. So the motivation for this presentation is considering what would be needed for the success of AUKUS. And one of the things that needs attention is the need to create a nuclear safety culture. That's an essential element in any nuclear work. It's not about military applications or other. And if it's not recognized, it can be a trap, and which can lead to bad outcomes. And I'll provide some examples for that. And so in setting up AUKUS, my suggestion, gratuitously offered, is to consider what you do to create this nuclear safety culture. It's something that doesn't happen automatically. And we've got examples of where it wasn't done and it led to unfortunate outcomes. And so I want to suggest that for AUKUS and for other nuclear things that are undertaken in Australia, perhaps in the future, that this should be an element, a key element in the combination of parallel efforts required to produce success. So that's my overall message. Let's go to the next slide. Okay, let's see. Hold on a minute. We're looking for page 2. Okay. Okay, so we need to go up to the top of the page. I'm only seeing about the bottom 2/3. Can we do that? Hello? No, keep going.
So I've got...
there we go. That's what we want. Okay?
Which previous? This one?
Hello?
I'm on the creating a nuclear safety culture slide.
Right, exactly. And so the key thing to note is that, as it says here, nuclear systems can be dangerous. And there are 3 important things you have to do. One is to control the power. The other is dealing with highly radioactive nuclear material and shielding of personnel, which is required for work in much of the nuclear environment. These all have to be done simultaneously, and they add costs, they add delay and difficulty. But it's part of just dealing with nuclear reactions. In particular, controlling the power has been done pretty well. But there have been some examples where it wasn't done, and I'll mention them before I'm finished here. The thing to know about power in a reactor is that it depends on the population of neutrons that are bouncing around inside the reactor volume. And it's just like a population dynamics problem in many systems, where the rate of change of the neutron population varies exponentially in proportion to a growth factor, which is conventionally called a reactivity, and also the population at this moment of neutrons. So as you add more neutrons, the rate of growth also goes up. And so in the extreme case of a nuclear weapon, that is an out-of-control version of that with nuclear systems for either propulsion or power you have a population which is controlled, and if it's kept within the proper bounds, things can behave stably and so on. And this is basically, if you want to increase the power, you go to what's called a delayed supercritical condition, which means that for every neutron born, a little bit later, more than one will be in the population, and so on. If you go far in that direction, you move into a domain called prompt supercritical, and the rate of change between generations of neutrons becomes much more rapid and much more like what you have with a nuclear weapon. So that's one of the things that's very important to avoid, and I'll come back to that. So when we look at the experience with submarines, in the US, we've had two submarines which were lost, the Thresher and the Scorpion. You see that these both occurred in the early or mid-1960s, and since then, largely the submarine program has been pretty much without drama. At the other end of the spectrum, you have the Russian and Soviet navies, which over the same period of time, roughly speaking, have lost 9 submarines, at least according to Wiki. And the thing that is really important to recognize here is that in addition to the direct costs, these failures are severely punished. And we saw that with the 3 Mile Island accident, which I'll come to in a moment. But that's part of what you try to achieve by building this nuclear safety culture, is that you avoid the conditions where this punishment would logically follow. Let's go to the next slide. Okay, so these are the attributes of what you look for in a nuclear safety culture. And that is, from the beginning, you have to create it. You have to have a concrete plan for how to form it. And the goals I've listed here are, in nuclear, you have to get good results on the first try. The usual learning experience where you try this and you try that and you learn from your mistakes and so on doesn't work nearly very well in this environment. And you've got to empower the individuals involved so that when they see the need to do something differently in order to support getting good performance, that they will intervene as needed and get the support from their colleagues to do it. And this really means operating without silos to the extent that it's feasible to do in human endeavors. So these are the goals. Stating them is easier than achieving them. And I would say that the methods for how to create one of these cultures is really to examine the successes of other high-quality nuclear safety programs and to figure out what they did right and find ways to imitate them. In the US and in Europe and North America, this has been done building especially on the experience in the navies of the US, the UK, and France. And in other countries where they didn't have the naval base to invent other methods to achieve the same thing. And I cite here the examples of Canada, Sweden, and South Korea, for example. That's not the complete set, but these are the ways to go about it. And so this has to be considered in planning whatever is undertaken new in a nuclear program, and that would include AUKUS. Okay, let's go to the next slide. So for success, this is what needs to be done. First, you have to realize what your goals are. You have to figure out what means can achieve it, and that's where studying successful prior examples is important. And to get a clear understanding of why both naval and non-naval efforts have been successes or not. So I review here the US experience using nuclear energy, where the naval propulsion program that is used worldwide began in the US Navy and has now spread to many other navies as well. So it began with the Atoms for Peace program, which came eight years after the end of World War II. It was announced by President Eisenhower at the United Nations. And it was to be focused on peaceful applications of nuclear energy. And this meant nuclear power plants, it meant nuclear medicine, and non-military applications. It also led to the first nuclear-powered submarine in the world, which was in 1954. And soon after that, the handoff of the nuclear propulsion technology to US utilities for power production occurred. So that 3 years later, you had the first nuclear power plant at Shippingport, Pennsylvania, which came online in 1957. So only 3 years after the Nautilus. But this could happen mainly because it used the same technology as in the nuclear propulsion system. And so essentially what you had was a nuclear propulsion system put on land and connected to an electrical production system. Later in the American experience, the next big event was the 3 Mile Island Unit 2 core melt. There were 2 units on the site, and I'll come back to that. And that led to the formation by a utility coalition of the Institute for Nuclear Power Operations. And this is something that I think would be very important to study within the AUKUS context. It came about because the CEOs of the companies involved gained consensus that it was essential to ensure that another 3 Mile Island-like event would not be repeated. And so they looked for ways to see that that would come about. And that led to basically a privately formed institute, INPO as it's called, for seeing to it that successful operations could occur. But their insights are applicable to almost any nuclear operation. Let's go to the next slide. One of the problems when the transfer to energy production facilities was made, at one time, there was a view in the electric power industry that nuclear was just another way to boil water. And this could not have been more wrong. But it was a symptom of the fact that culturally they were not ready to take on the use of such a demanding technology. When INPO was formed, and this was done at by the decision-making of the utility industry, not of the government, basically they did it using many alumni out of the US Navy. And I'll talk about why. So INPO has largely used a command and control structure such as you find in military organizations as with the Navy. Let's go to the next slide. I think we skipped one. Yeah, we should be on page 5, yes, okay. So the example in the Navy was one that was created for the control of nuclear-powered surface ships, primarily aircraft carriers. And the reason is that the Navy requires the commander of an aircraft carrier to be a flyer, that the primary mission of that ship is to be able to put airplanes into the air and keep them there as much as the mission requires. But the captain or the admiral basically also has responsibility and decision-making authority over the propulsion system. So he's in a position to make decisions about the propulsion system. And there was concern that since the flyers usually did not come out of power production, that they would make well-intentioned but erroneous decisions. So they created a course for people taking these kinds of command roles to become proficient in understanding the system that they were dealing with and to make wise decisions. When INPO was formed, the same model was used. And so with INPO, what you have is a program involving all of the nuclear power plants in the country. The things that they offer, which were not previously available, are evaluations of performance and assistance in improving performance, should the evaluation indicate the need for it. And also, they play a role in whether the power plant can get liability insurance. in that there's a tacit agreement that the insurance will not be provided if the evaluation scores are too low. They also collect data concerning the performance of the nuclear fleet. They provide analyses of important events, such as a transient or an accident, and they make sure that it's communicated to all the other INPO members. Before 3 Mile Island, these things were not being done. And so the point of INPO is to facilitate improvement in the quality of operations. The things that they do are to offer training. There are 12 courses that they put on, and we run 2 of them at MIT, where I'm the director. And also there are executive level performance reviews where the CEOs of the different companies are required to explain why they got whatever evaluation scores they got to the other CEOs. And especially those who get bad scores find that it's a pretty humiliating experience, and it seems to motivate attempts at excellence. So these are things that INPO does to try to improve performance and provide incentives for the organizations themselves to take command of their own fate. Okay, let's go on to the next slide. Okay, so after 3 Mile Island, there were several things that were done. One was the formation of INPO, the creation of a biannual plan for evaluations, creation of courses ranging from plant operators to members of the corporate board to make sure that they're well informed concerning what they need to know to perform their functions, providing technical support and information sharing, and providing the evaluation scores that play a role in the insurance certification, which I mentioned before. It also led to a rethinking of human capabilities and accident response strategies, because fundamentally, the 3 Mile Island accident was a failure of the staff to understand the situation that they were confronted with and to make the right decisions and actions. They are not necessarily to be criticized for this, because the way that the plants were designed in those days made actually being successful in this area more difficult than you might hope for. It led to, through that, it led to a redesign of all the nuclear power plant control rooms in the country, the permanent addition of a shift technical room where that person's job is simply to observe what's occurring and to offer advice to the operational staff. This person does not have decision-making authority, but rather is to provide a set of eyes and the opportunity to think more clearly about what's going on. Another thing that is done, which you don't see in every other country, is the requirement for plant-specific later and their frequent use. 1 week out of 5 is devoted to training, and the rest to operating the power plant. And finally, reformulation and flow charting of plant procedures. So these are all concrete things, activities in the running of power plants that became important. Okay, so on this slide here, we're talking about the Chernobyl event, which occurred in 1986. And it's a very interesting one because it was the second occurrence of a prompt supercritical transient, which I spoke about earlier. That is, amazingly, 8 months before Chernobyl occurred, there was a refueling accident on a Russian Soviet submarine near Vladivostok, and it led to a prompt supercritical event resulting in 8 fatalities. And rather than being the trigger for a reevaluation of how reactivity events could be managed, this was apparently not communicated in an effective way to the power plant fleet in the Soviet Union. And so 8 months later, you had essentially the repetition of the same type of problem with the Chernobyl accident, where basically proceeding in an improvisational and somewhat uncritical way, the operational crew put the plant in a vulnerable condition such that as the operations continued, a prompt supercritical condition occurred, and it led to the explosion of the reactor and spreading of its fuel and materials around the reactor building, and release of much radioactive material in a plume that eventually reached the stratosphere and led to flows all over Scandinavia, across Poland, across Belarus, then to France, then to Greece, and then finally around the world. And that led to the formation of the World Association of Nuclear Operators, WANO, which was done deliberately in imitation of INPO, but without many of the strengths of INPO. So they have headquarters in the cities that are listed on the screen, but on the major continents where you have nuclear power fleets. And their focus is on the international nuclear power fleet, but not on the one in the US, and some that are allied with INPO, such as the reactors in South Africa. And WANO offers evaluation and assistance, but it lacks the levers to see that there are consequences that flow from their evaluations. There's also communication among the different sites, but in a less deliberate way. And cultural differences between the various countries which are involved tend to come into play in important ways. And with INPO, you've got a system which can be pretty coercive and can enforce rules. With WANO, it's much more consensual and less effective. So that's what we have operationally. And so let's go to the next slide. This is my last one. So I'll end by saying that creating a nuclear safety culture is essential in any nuclear enterprise. It must be shared throughout the entire nuclear enterprise, and explicit enforceable tools are needed based upon the experience of successful examples. So that's my overall message. And I suggest that this be made an element of the planning work in formulating AUKUS and deciding what to be done. Then, if there is interest in Australia in going beyond naval propulsion, but that first enterprise can be successful, a good foundation for considering other options could be in hand. That's all that I have to say.
Michael, thank you so much. We're in a pretty lucky place where we get to learn from our partners and allies to see what mistakes they've made along the way and ensure that we don't make those same ones. Are there any questions from the audience? No? I'll let you get to sleep.
Well, I guess there's a panel discussion.
Yeah, you're welcome.
I'll be around for that as well.
Perfect. It'll be great to have you on the panel.